All right, so I don't believe that providing absolutely all the details of a system like DNS matters that much. I want to stick with high-level principles. So I will discuss high-level DNS. I will discuss at a high level something like LDAP and some other ideas. But I don't want to go into too many details. You can always Google for details. If you really, really care about the protocol, what matters is how do you design such things? And how do you stick with some reasonable subset of principles to keep the whole thing together? And DNS, like anything else, was essentially done in a hurry when they realized they have too many computers, and then it essentially evolved, right? So I mentioned this to some of you. If you believe that most of the things around you are the creation of very careful thought, that's not necessarily the case. I mean, it's just some engineers, a couple of days before the deadline, decided to do something so that it kind of works, and then that influenced 30, 40 years of stuff afterwards. Okay, that definitely happened with almost anything related to the web, for example. All right, so we talked about namespaces. I mean, naming in general, and namespaces are supposed to put some sort of order in there, right? So you create some sort of a hierarchy. Why? Because people like hierarchies. I mean, we are hardwired to do hierarchies, right? And you can form hierarchies based on all kinds of criterions. We're going to come, when we talk about LDAP, and especially attribute-based naming, we're going to get closer to something like search, right? That's a different story. But when it comes to hierarchies, it's like directories, right? You have broad categories with subcategories, subcategories, subcategories until you get to some smaller resource. Now, initially, all of these things were supposed to map some sort of an existing hierarchy, but things got disconnected very fast, right? So, for example, who should be in the .com domain? I mean, initially, .coms were just businesses in US, and now whoever has $11 can buy a .com domain. I mean, that's really the way it goes, right? So, all right. So let's go into some details about DNS and how this might work. And this is, in fact, happening all the time on any device that has wireless access. Very few devices stick only with, say, IP addresses. I mean, some of them might actually be, for example, embedded processors into drying machines, right? I mean, maybe those, I mean, they start to have internet access on refrigerators now and things like this. Maybe you have just a low-level IP address implementation in some of these embedded devices, but for the most part, phones and anything upwards is going to go and use the DNS, right? So the way this works is if you're trying to access some URL, in this situation, the URL is already broken into components, right? So what's the separator in URLs? The dot, right? I mean, that's a conventional separator, at least for the first part of the URL that's supposed to determine the machine, right? So in this specific situation, FTP is the protocol, and the address was probably reversed, right? So let's write it on the board. It was really something like FTP, I'm sorry, colon, you have 2 slashes, yes, colon slash, I never quite remember. So colon slash, and then probably it was CS, VU, NL, and then some other information. This is going to be parsed by some middleware, some library, really, okay? And when it's parsed, it could look like what we see in there, right? NL is Netherlands, right? The textbook writer, Tannenbaum, right, is faculty at the University of Netherlands. I have to remember the university, right? So then all his examples are with Netherlands. Okay, Netherlands, then we said VU, CS, FTP. And all of these components can be thought of as being some sort of, if you want, directories. So this is a so-called top domain, right? We had a picture before of how the top domains look like, right? These are examples of top domains, .com, edu, gov, mil, and then countries have domains and so on and so forth. VU is going to be a subdomain of the top domain. Now, how these domains are administered and managed and so on and so forth, it's a very, very complicated kind of procedure, right? And to some extent, nobody quite knows in the end who's doing what because of all the crazy setup, right? But in principle, they separated the top domains, and they have different management for each of the top domain. And then you essentially have to pay or beg somebody to let you plug in translations in a particular top domain to get subdomains and then subdomains, so on and so forth. Now, an interesting question is, OK, so you have this domain, subdomain, sub-subdomain, and this is something related to the protocol, but who's doing what here? I mean, that's the most important question. And if you think about it, this is related to the question of specifically how the translation happens and specifically in which ways you can actually have control. Right? Now, these details can, in fact, matter a lot, especially if you have problems. Right? So when it works, it works. It's like any other thing, right? So for example, when your car just runs, it runs, and you're happy, and everything is fine. Or you're not even happy. You're just there. But when it doesn't run, right, then you're in trouble. And if you're far away from a mechanic, you might even pop up the hood and start asking questions about how does it work. Maybe it just needs a hammer somewhere, and you can smack it. It doesn't work that way most of the time. It's the same thing with the DNS. I mean, when things go bad, it might be important to start looking at them. And on the other hand, you might have to do something like this yourselves. So for example, to some extent, the Napster people had to do something like this. I mean, they had to partition the world into pieces because the servers were getting overwhelming and so on and so forth. So the translation might happen in the following way, right? So you have to contact somebody. So we are talking about a translation. Somebody has to provide a translation. So who has to provide the translation? Some sort of a server. Right? So in this world, we really have only two kinds of ways to get things done. One is client, and whose client and whose server we've seen, it can be upside down when it comes to certain protocols like X, right? X Windows protocol. So the client, namely the application that needs this done, has to contact the server and ask the server, can you do this for me? Now, the server itself might contact other servers and other servers and other servers if it's a really complicated protocol, or might just say, yes, I know what the answer is. Okay? So this is really what's happening in here in order to resolve the name. This is DNS terminology, right? So resolving the name means find the corresponding IP address to this name, because that IP address then is going to go in all the packets that are sent to that specific machine. Now, there is a little bit more beyond this, namely, well, it's kind of captured by the FTP. It's what's the port number. And through essentially conventions, global conventions that are de facto conventions, nobody sat down and made standards out of it. Eventually, they do maybe standardize some of them. FTP, in fact, indicates the port number, which I don't remember what it is. I know SSH is 22. HTTP, it's 80. FTP, 20, 21. All right, here we go. Right? So port number in this case, 21. Why 21? It's the number that comes after 20, really. I mean, they've done weird stuff when they decided some of these things, right? Why 80 for HTTP? Why 443 for HTTPS? It was in the way. I mean, so it turns out, I believe that it's important to understand that sometimes these decisions were purely arbitrary. So asking too many questions about them is going to get you nowhere, right? I mean, literally, somebody had to decide at some point is we need a number that's not used. Any ideas in a small office? OK, let's pick this. It sounds good. Done. Is it used? No. Good. Let's use it. Literally. OK? Good. So the way the translation can happen is the client's name, the client's, if you want, middleware, the library, is going to break it into pieces. And depending on those pieces, it has to talk to some server and say, can you help me translate this? OK? And what server? Well, any machine, and this is one of the problems that can happen with, for example, internet connections. Any machine, any client, any device that wants access to the internet must have not only the actual low-level machinery, right, which is run that ARP protocol and whatnot to convince routers to route packages, but also have a so-called DNS server name. Well, it cannot actually be a name. It must be an IP address. So the idea is the following. If I have the IP address of a server that can help me translate, then I can talk to that server to find the mapping between nice names and the IP addresses of the rest of the universe. But you see, this is a bootstrapping strategy, right? I grow from one IP address to mapping for the entire world between nice names and IP addresses. But I must know one IP address. Okay? And that begs the question of how do you know that one IP address? There's a counterpart problem, which is not pointed out in this textbook or any other textbook I know of. For example, for a peer-to-peer network, you must know one participant in a peer-to-peer network, right? And then you can bootstrap and go and do other things. Okay? So how do you know the IP address? So at the core of everything is you must know the IP of one or more DNS servers. Now, of course, the DNS servers must know other DNS servers and other DNS servers and other DNS servers to get you what you want, or know about the entire internet, which was the case at the beginning. Right? When the internet was small, they needed only one DNS server. Okay. So, for example, do you know on your phone what the DNS server is? Oops. Okay. So these things are so important that they now get bundled up with the discovery protocol, right? So when your phone, take a networking class to see all the details, but when your phone connects or your computer connects to a network, because this is so annoying to get some administrator involved and so on, you have automatic discovery protocol in which you're really saying, hey, I want to be connected on the network, but that's some kind of a low-level Ethernet protocol saying, hey, I need some IP. Oh, if this is not taken, I'll take it. Okay? And then you're running some low-level protocol in which you say, is there anybody that can help me bootstrap the entire system? And this is what BootP and DHCP are all about. These are discovery protocols. And then presumably some sort of a DHCP server nowadays, because BootP is really not used, right, is going to say, hey, I know, first of all, I can assign you an IP address so you can be part of this internet thing. But I also can tell you about the DNS server, right? And if you want to do a translation of names, go through this DNS server and go and do whatever thing you want. Now, just as an aside, for example, because the DNS server is so crucial, you actually know, you can actually tell and monitor internet activity by just logging DNS requests. Forget about the traffic and whatnot. But just logging DNS requests, you know exactly what's happening and how it's happening and whatever. This is why there are basically two efforts, and you can see them now. One of them is to encourage people not to use the DNS server from their ISP, right? So there is an interesting project called OpenDNS. And guess what this is? You go and by hand change the DNS and override the DNS that your ISP wants to give you and say, you know what, I want to use this specific server, the OpenDNS server, or one of the known OpenDNS servers. That means all your requests, instead of going through your ISP, as it would normally happen, will go through the OpenDNS. Okay? And another effort is so-called encrypted DNS, right, through IPsec and other things, in which the entire lookup process, because ultimately, when you say, I want to map NLVUCS FTP, that's some sort of information in a packet that moves over the internet, which could, in fact, be intercepted and looked at and so on. Of course, if it's encrypted and you're using some kind of a cryptographically secure method, then only the OpenDNS server can, in fact, understand what you want and send you back an also encrypted reply. Now, they can still see what IP addresses you're accessing, but again, DNS servers are so much more interesting. Okay? Now, why is this even possible? Because it's all in this library. It's in the client library name. DNS is like any other protocol, and in fact, uses IP. I mean, it's not built on TCP/IP because there's no need to do this. It is yet another protocol built on top of IP, right? So at the bottom, you have the dark side with Ethernet and other low-level protocols. Then you have IP, right? This is the protocol that allows routing of packages. And on top of it, you have TCP. You also have UDP, and we did talk about them. And some other protocols that don't really need a full connection and things like this, right? Sometimes these services will use TCP or will use UDP, but sometimes they are going to do their own variant on top of IP, right? And I believe the DNS is here. Well, maybe they switched, actually. Do you know if they switched and it's TCP? They switched to UDP. OK. Now, there are some details that don't really matter. They are more curiosities, right? But some people happen to know too much, so I have to be careful. So I ask. OK. Right? But you do have a choice. I mean, you could do your own version of an IP protocol here, right? And that's actually happening with some of the services. OK. So client contacts a first DNS server. The DNS server will then try to figure out if it can map the address. Okay? And at least if it has never seen all the decimal points in the address, right, it needs to, in fact, contact other DNS servers and other DNS servers and other DNS servers. Why? Because you would not expect a single server to deal with the entire internet. So this is, in fact, a form of hierarchical organization of a set of servers in order to provide, in this case, a planet planet-size service, right? So in fact, all the DNS servers, at least in the non-dark, in the light internet, right? So they talk about, for example, dark internet. And you can imagine if you can have your own private DNS servers, you can have secure connections through cryptography and whatnot, and apparently some hackers use that. That's really a parallel universe, and you might not even be aware it exists unless you do deep packet inspection and things like that. But at least in the visible part of the internet, all the DNS servers are in fact connected to each other through a hierarchy. And that does make sense, right? So let's draw some kind of a picture here. Right? We have a similar picture in there. But essentially, I can have a DNS server to deal with a so-called domain. This easily can have thousands, or sometimes tens of thousands, hundreds of thousands of client machines, right? Or servers, or whatever else you want. But definitely doesn't usually grow at the level of millions, and not the billions that we have now in the entire internet. Now, these servers themselves, when there are requests outside their core domain, might contact high-level servers and high-level servers. Now, what's going to happen is, as you go high up in the hierarchy, you only know about the level right below you. You're not going to know all the details. For example, this server is not going to know about all of these machines. It only knows about all of these subdomains, and might itself manage a large number of such subdomains, right? So in this situation, you would expect to have a CS subdomain, and possibly any machine, for example, in our department, that's going to happen, right? We have our own DNS server. So if you go through the department network, they're going to say, hey, select this DNS. You could do OpenDNS, by the way, but you could say, select this DNS. And then essentially we have a department DNS server. The department DNS server then is connected to the university DNS server that controls what domain. So in our case, right, this is going to be CISC. What do you think is the domain at here? UFL, right? So this is controlled by the department. So you see the hierarchy? This is the university in our case. And what's the top domain here? EDU. And this is controlled by whoever controls the EDU domain, which, again, it's sometimes hard to tell, right? Of course, EDU is the university domain. Because a lot of this research, a lot of the initial research in the internet was done at universities. Universities made sure they have their own domain. This is almost unheard of, right? Everybody else gets maybe a country domain if they are nice, and that's about all, right? But not in US. We have a domain for whatever we want. OK. Right? So what's the, for example, other interesting domains? The gov, right? And the mil, the military. They have their own domains. They are draconic about how they actually protect them, so on and so forth, right? Good. So at the very top of the internet, you would expect to, in fact, have these domains, but there must be one or something at the very top. Now, I want you to understand that you don't necessarily need all of these servers all along. You just need to provide the illusion that those servers exist. For example, at the very top, you might not, in fact, need any topmost DNS server. And in fact, it would be wasteful to do so. All you need is to make sure that all the top servers keep in sync the information, right? What kind of information? Well, the information is which other server to ask if the question is not about something you know of. So what would happen is, for example, if from my, let's say from my phone, I live in this domain, right? CISC, then UFL, EDU, right? All the top domains somehow know about each other. And what would happen if I'm trying to go to CNN.com, which is in a completely different domain? Well, what would happen, presumably, is I contact the local DNS server. Let's assume nobody has ever heard about CNN, because caching makes it all a lot more fun. And I'm going to talk about that separately in a second. So I contact my server, and it says, well, it's not in my domain, but I know who to ask. You ask the UFL. Well, we are not in the .com. You ask the EDU. And it says, well, we are EDU. You're asking for something in .com, but I know the address. I know who to ask about the .com. Right? So if you keep in sync the topmost DNS servers, and they know about who to ask for another domain, then you just jump now at the same level of the hierarchy to the .com. And .com will say, well, I know about .com and whatever is immediately below. So what are you looking for? CNN. OK, good. So I can contact the CNN DNS. and the CNN DNS will look up www and say, I know about it, and maybe resolve it immediately. Or if you have a deeper hierarchy, as it is the case here, you go down until you find out about the machine you want. So in fact, the way things are going to go in DNS could be you do first a lookup all the way to the top, you go on peers, you go all the way down to find who knows about that specific machine. You could get an answer that says that machine is not mapped. Or you could get the proper answer, and then the message comes back. Now, this is already a very long way. This is why you want to do caching on a large scale. Right? So for example, when you go on CNN's webpage, everything is CNN.com one way or another with other decimal points. Right? So you have to cache, because otherwise it's exactly like the virtual memory to physical memory. You do more work translating than you do actually getting all of the things that are on the webpage. Right? Browsers now support deep inspection of what is it that they are doing. It's quite an interesting exercise to ask the browser to actually show you just how many little things it gets independently or not, and even how fast it gets them, in what order it gets them. Right? Easily, you can end up with tens to hundreds of independent connections to grab just something that looks like a normal HTML page. And some of them go to completely different domains like doubleclick.com and whatnot. Okay? All right? So is it at least a high-level idea? Is it clear what's happening? But each of these guys is, in fact, some sort of a database machine, right? That's going to do a mapping between the name and who has more information, or the actual IP address. This is really the idea. Now, in the good old days, the IP address carving, who gets what range of the IP address, was also reasonably hierarchical, right? And this is why the DNS protocol itself is designed so that you can actually get ranges for such IP addresses and whatnot. Things are more and more and more fragmented, so these servers themselves had to get more complicated in order to do the mapping, right? On the other hand, the computers got much faster, so if you think about it, even in a single machine, so ask yourself the following question, and this is maybe a question for the database class, but with a single server you can buy now, let's say that costs a couple of $1,000s, how many names could you resolve? How many things could you know about if things don't change, let's say? Well, even if you just want to keep things in memory, you can easily keep hundreds of millions. You can do some math if you want, but $1,000, let me give you just some food for thought. $1,000 buys 128 gigs of memory. 120 gigs of memory is a lot of memory, right? So if you keep about 128 million, let's say, you would have 1 kilobyte per entry, and there is no way you need a kilobyte per entry in this kind of circumstance. So easily you could keep 100 million in a machine that's only $3,000, $5,000 at most, right? So even large domains might not suffer in a significant way. Right? For example, UFL domain probably doesn't have more than 1 million entries in it. Well, actually, named machines, you have far less. You probably have in the order of 10,000. Your phone could really resolve. You could keep all the 10,000 in your phone. Now, you do have another problem, which is an update problem. Things keep on changing. And how do they change? You change the configuration of the servers. So you need to think about, and this is maybe where things get more subtle, you need to think about, OK, you do caching, but you need to invalidate caches. And this becomes a very, very important issue in general. How and when do you invalidate caches? That's one issue. And the other issue is how do you propagate the updates? Right? Because DNS is controlled hierarchically, things are a little bit more ordered. But a particular way to speed things up, and this can actually be done at any intermediate point, right, is to do massive caching. For example, the top edu domain, of course, has to know about the peer domains and what's immediately underneath. But nobody says it should know about a lot more than that if it could resolve things faster. It's not so important to do it here, but it's very important, for example, to do it here. You can significantly improve user experience by caching much more at the DNS server that you have in here, right? Now, since the vast majority of the people tend to roughly, again, you have the 20-80 rule, probably with different proportions, right? How many top domains people go to? Maybe, you have super popular 100 to 1,000, and then lots of little crumbs, and then you don't necessarily quite care about that. If you cache the top domains, most of the people would never make it, for example, to the Apple's DNS server, because the UFL one intercepted it and already knows what's the top IP address for the, I don't know, apple.com, let's say. Okay. Not to mention facebook.com. Okay. All right. So that's the story with this. So there is some sort of a request that goes possibly all the way up to the DNS hierarchy and comes down with all kinds of caching in between. Now, you immediately can imagine that you do want to do caching on the client itself, right? And that becomes very important. So the library itself is going to do its own caching. So caching happens at all levels of the hierarchy. The library does caching not to keep on doing DNS requests. Then this server does caching, this one does caching, this, God knows what this does, but does all kinds of things, right? And all the way down. Yes? Yes. So let's think about the Akamai and what Akamai does and how things are. Now, what Akamai depends on in a crucial way is intercepting DNS requests and routing them to a different place. Right? So I mentioned Akamai before. What they are trying to do is place servers that serve content at the ISP in order to cut down on the entire traffic. But you see, they have to figure out where you want to go and send you to the local server. So the question is, how do you do that? One specific candidate for this is, in fact, DNS. So if you actually use the DNS server, and by the way, this is one way to completely provide an illusion of a parallel universe for the internet. This is why OpenDNS was, in fact, created. Because by doing DNS manipulations, you can create the illusion that they go to CNN, but they actually never go to CNN. You're just a website that looks like CNN, right? If you can mess with DNS entries, you can do phishing. You know about the phishing security, right? Exploit. You can do phishing on a very large scale. I mean, how hard is it to make something that looks like CNN? Not as hard as you might think. You dump some of their pages, you do some of their stuff, and you can create the illusion that you have a CNN. Right? Now, CNN is not interesting, but Bank of America is. Right? You say, type your password because I'm going to let you see your account, and then say, oops, technical error, but they got your password and cleaned up the account in the next few milliseconds. But by the way, as incredible as it might seem, I might as well tell you about the side story. This is one of the more incredible things. Now, it's hard to do this with Bank of America because of the security certificates, which you're going to get more details in the networking class and so on. So those supposedly are unforgeable. But apparently some people in Romania, right, lots of extremely bored, extremely skilled people in Romania, they, in fact, designed a full-fledged ATM machine that looked incredibly accurate. And they placed it in various places in Bucharest. And people went on to take money out. The machine was basically just recording a PIN number and account number for further bank account cleaning purposes, right? So they literally took the trouble to have highly credible menus, very interactive, very nice. They probably could have even sold the application, but they used it only to trick things. In Gainesville, we had incidents like that. Okay? So DNS becomes a crucial part of the security infrastructure. You go to the wrong DNS server, you can be routed in very ugly places. So to come back to Akamai, what you could do is try to intercept it at a DNS level. And that's happening, in fact, quite often when you try to detect from what region people actually come. There are now services, actually. You can tell by the IP address where they come from and route them in a completely different place. So nobody says that this DNS server should be very rigid, relatively straightforward little things. I mean, I want you to make the difference between the protocol itself, in which you're making a request and you're saying, please give me this mapping, and what the server does. The server can do whatever it wants and can do very sophisticated things. Things exactly like this is, oh, you know what? I know of this Akamai server that's actually at your ISP, and I'll give you the IP address of that Akamai server. And to you, it looks like CNN because it, in fact, has the CNN content, which is propagated within whatever number of seconds, because that's why CNN pays Akamai a lot of money, right? That's one way to do it. There are other ways to do it using some sort of much lower level protocols with IP forwarding, right, and stuff of that sort. But the DNS is by far the most convenient and more reliable way to actually do this. Okay? So be careful with especially the mapping between names and things. This is why, for example, you might get a very different web page within a certain network and outside the network. I mean, probably one of the more notorious cases is the Best Buy case. So in every store, Best Buy got in a lot of trouble for this. So if you go to bestbuy.com from the internal network, you actually get a completely different website than the bestbuy.com when you go to any other network. The most important thing is not the looks, which are identical, you can't tell, is the prices. Right? This was designed specifically for people that check prices on whatever, bestbuy.com and so on. And because every store manager has the ability to decide on what prices they have and what not, they said, hey, why not take it all the way to DNS things and whatnot? So they give you a special version of bestbuy.com. Right? And again, there is no way to tell unless you use your phone through 4G, connect to Verizon, who's not friends with Best Buy, to do the hijacking, but they could. Right? And then you see the real version of, let's say, the bestbuy.com. They could, in fact, then provide a complete illusion for other websites. All you need, actually, is to watch the traffic. So even if you have normal traffic, since you can intercept traffic and modify traffic, right? They do this, for example, to inject advertising. Then essentially what you can say is, hey, I'll increase by 10% all the prices if I can detect how the prices are stored in the packets. Is this hard to pull off, but possible, right? When you look at Amazon.com, I'll simply increase by 10% any price that Amazon displays by modifying the numbers that come on the wire. Right? Big stunts like this were pulled off by the hacking community in various circumstances. It takes a very specific kind of determination, but it is possible. So it can be very dangerous to talk to the wrong DNS server, and that becomes very important. Now, this kind of things could be useful. This hierarchical organization can actually be useful in circumstances that have nothing to do with the DNS and mimic what humans were doing for a very long time. I mean, think about how large organizations are organized. Right? Well, I mean, reasonably close to this, right? You have, if you're a low-level programmer, right, you have a boss, your boss has a boss, your boss has a boss, has a boss, has a boss. If you need to talk to another programmer in a lot of the organizations, you have to go all the way to the chain and down the chain and get approval for everybody, and 6 months later, maybe you meet the guy that could help you in 5 minutes. Right? So this is the problem in any big organization. And to some extent, it looks like it's the same here, but again, you could cache maybe that, and who can help me, and then later you just contact that person and so on. So naming becomes very important in normal human interaction, and not only through this. Obviously, quite often, you're going to see mimicking things that we were doing before computers reflected in some of the things we do with computers, but with some kind of added benefit. OK, so let's see very quickly. Right, so you can see all the details. I mean, if you really want protocol details, which I don't care about necessarily in the class, I care about the high-level ideas, go on Wikipedia and Google and find, OK, I mean, the protocol, it's extremely specific, and there is a large standard that specifies exactly what DNS servers should do. But it's highly irrelevant in that, unless you want to implement your own DNS server. OK, so this is how things could go. Right, so you're going to have interaction with these nodes until somebody knows about that IP, cached it. Right? Now, in DNS, in the standard, you're going to have types of records, how those things are specified, configured, what do they do. Again, there is even a shift. They keep on switching to different substandards and things. So it becomes not particularly important to memorize this. So I don't want to go through this. Let's talk a little bit about other kinds of hierarchies, for example, LDAP. But maybe even more interestingly, I want to spend more time on that, on attribute-based or search-based naming. Okay? So LDAP is some sort of a souped-up phone book. So LDAP is about finding people, not finding machines. Right? We had the DNS for finding machines. Think about finding phone numbers for people. How do you do that? Well, let's ignore search. Search is, to a large extent, cheating. So why do we need search? Because the normal way to find something is too cumbersome, it takes too much time, and then you say, find some sort of an approximate mechanism that maybe gives me the right answer, and we call it search. Okay? But if you want, for example, to find the phone number, so think about good old days, okay, in which everything was on paper, say. Okay? I mean, we had phones for 100+ years. And how would you find the number? Well, you could, and this actually mimics maybe even DNS, but definitely LDAP, right? You could basically let's say you do it through the phone, right? You could call some kind of a special local service to say, I need you to help me find some person. They would say, OK, so where does the person reside? If it's that town, they say, OK, we have our own book in which we look and give you immediately answer. But if not, I'm going to call my counterpart in another town, which might call the counterpart in another country, which might go up and down the hierarchy to find who might know the name of that person. Now, of course, God forbid if they moved from that town or you didn't know in what town they are in the first place, right? So these things can become very cumbersome. It's the same thing with the DNS. So I don't know how you feel, but personally, if I make a small mistake in the URL and I get no such URL, I get annoyed, right? It's like, hey, figure it out. And this is why Google does what? Did you notice? Almost anything you put in there first tries to do the normal thing. And if it doesn't find it, it throws it in the search pool. And the search is actually much more robust. It's approximate and so on. And they come back with, did you mean the real URL? And of course, I say yes. Now, that encourages very reckless URL typing. I don't even bother to look at what I have there, or I don't even bother to format it like a URL. I just throw in a bunch of words that I know are going to get me close to the search and give me within 10 results. And most of the time, I'm feeling lucky and just click on the first one. So you can see how search could actually be almost a full substitute for name service. Okay? So LDAP started when computers were not so good at search, before the Google times, right, in which we had Alta Vista that were not particularly good at searching. And then they tried to put a lot of structure into it, right? So you want to get some sort of a hierarchy that could be related to country, locality, organization unit, so on and so forth, and then extra information about people. And this is essentially a very detailed phone record-like thing, but you associate information about users that's maybe not only phone numbers, but IP addresses and all kinds of other things, right? But in essence, it's very similar to the DNS, right? LDAP was introduced for very large organizations, and you might, in fact, have multiple such LDAP servers talking to each other very much like DNS does. But it's a different protocol that caters to a slightly different usage scenario, right? And first of all, it's not controlled by the organization that controls DNS. Sometimes you need to implement almost the same thing just because the wrong people control the thing you're trying to mimic, okay? All right. Details, again, don't matter that much. The important thing is all of these lookups do happen, and somebody that might know about what you're looking for is contacted. Very much like what was happening with the phone lookups in the good old days, except that it's much faster, hopefully. Okay. Now, LDAP was also introduced in order to manage passwords and access. So you can you can specify domains and who can access what and other things, right? To aid in authentication, which is a completely different issue that networking a class would cater to, okay? So again, you could have and you usually have a hierarchical implementation of an LDAP server in which, as you go higher up in the hierarchy, you contact other servers to help you resolve the names. But there is no global LDAP if you want infrastructure. LDAP is always something that an enterprise, a single entity does, and there is no connection with other LDAP servers. It's then fully controlled and fully managed by a single large organization. Now, of course, within the organization, you can have many subparts, and you need multiple administrators to take care of this, right? OK. And by the way, LDAP is, if you want, an open standard that tries to mimic what I think Active Service was doing on Windows, right? So Microsoft introduced their own naming service that, in spirit, is the same as LDAP. And it had a little problem that it only ran on Windows, and then people wanted a more generic solution that can span different operating systems, so on and so forth, and then kind of a big hullabaloo. Okay. All right. Now, when it comes to distributed hash tables, we talked about them, right? You have this peer-to-peer network, and it's all about naming. You can think about placing some sort of a hierarchy on top of that as well, right? That will alleviate some of the problems you might have with just knowing what the hash is for a specific resource you're looking for. If you can take the resource and you can map it to a hash, then you can do the routing. We talked about this last time, and that's going to be fine. But of course, you would like to have a little bit of a hierarchy to be able to say, you know what, I know most of it, but I want to list let's say it's in this directory or things like that. And for that, you need to implement some sort of a hierarchy. Now, there is an interesting paper in 2004 that explains how such a hierarchy could be implemented on top of peer-to-peer networks. Okay? I don't want to go into all the details. None of these things are deployed on a large scale. LDAP is, I'm sorry, but the distributed hash table hierarchical lookup is more kind of a research prototype implemented by some people to write a paper and not necessarily something that's deployed. So it's interesting, but knowing too many details about it is not going to help because no organization I know of is actually deploying these things. Okay? But it's possible. This is the important thing. Now, hierarchies do allow you to organize things better, not only to find things faster, right, because you have some kind of a fan-out in the tree, but also to organize things better in some sort of logical bundles. And that's one reason you might want, in fact, to have some sort of a hierarchy on top of distributed hash tables. Now, right? Oops. Okay. I should have had another. Okay. Let me talk about another topic that somehow there is no slide about it. This is closer to search, right? So we still have about 10 minutes, I think, right? So something that does become a lot more useful is something guided now by some sort of properties of the thing you're looking for, right? I think in the textbook it has a funky name. By the way, the one reason I'm not insisting too much on the terminology in distributed systems is because it's not particularly stable. You pick another book and it talks about things in a different way, and people in the research community can't really agree how to call things, right? So then what's the point of insisting oh, you must refer to this in this way, right? For big O notation, it's extremely standardized. The whole, if you want, theory community agrees on how to put the big O notation, but not for distributed systems. These people don't quite like this, right? So this is called, I think, attribute. One second, since I started. Well, it's something like attribute-based naming. The idea, though, is the following. I'm going to associate with every particular resource, instead of associating a so-called name, I'm going to associate properties, right? And I might have, usually you do want to have a mix between the hierarchy and so on. Now, if you look at the LDAP implementation, you can think of all the elements in LDAP as being, in fact, properties, right? So even though they do reflect some sort of a hierarchy, country, locality, organization, organizational unit, you can think of them as properties, and I can add other properties, right? For example, skill set. Now, this becomes very important, for example, in an organization, right? So in order to find somebody, you might think about and contemplate having a service in which you specify a set of, if you want, features, properties. It's something that looks similar to a query, and you say, find me somebody who fits this query. Now, this is an indirect way to look for specific resources, but in fact can be a lot more useful than a direct way. Any mistake in how you specify the hierarchy, for example, will immediately result in, yeah, we don't know of anything like that. We tried, it doesn't make sense, you're not going in the hierarchy, right? We contacted, so for example, typical mistakes are LN versus NL. I mean, good luck remembering that it's NL really for Netherlands, right? Or things of the sort. You make the slightest mistake like this, the result comes back and says, never heard of anything. I mean, there is no VU domain in LN. I don't even know what LN is or if it exists, okay? Versus you run a search, especially a search that's robust, especially a search, for example, what Google does now, that now tries to make comparison against queries. They actually match your query against other queries to figure out what you might have meant if there is no perfect match, right? So you have complicated scoring techniques to determine what the answer might have been, especially if you should always prefer perfect matches. But if you don't have a perfect match, some sort of scoring could actually get you much, much closer, right? And in that case, the search algorithm can say, you know what, I don't have a perfect match, but this looks good enough. Now, in a perfect match, other things can become as important as what you would normally consider the top domain, right? So, for example, in Google, maybe we can try this exercise. If I put a URL in which I invert just 2 letters, if this is something that some number of people were looking for, Google might know about such a query, might have run this approximate matching algorithm, but that's now based on properties. Well, it's more based on kind of text search, and say, oh, there is no perfect match, but here is probably a very good guess of what it is. Actually, Google does that so well now that they assume by default that you made a mistake. They give you the answer as if you typed the right thing, and they just put a little bit of a disclaimer at the top. and they say, did you meant and then the wrong thing? So they don't say, I'll give you the answer for the wrong thing you asked for, and they say, did you mean the good thing? They flip them because, again, they realize that most people do mistakes one way or another, and people are annoyed if the machine is not smart enough to figure out that they really wanted NL here. Okay? So then, interestingly enough, this kind of a search-based naming becomes far more useful and far more powerful than the traditional hierarchical naming. So more and more you see, in fact, a shift towards the matching properties, describe properties of what you want, so on and so forth, right? And once you get, as a user, once you get kind of hooked on that, there is almost no going back. You really only need, so I mean, if you think about it, if you know of enough characteristics of a certain person you're looking for, and if you have a decent search, you never really have to remember details, right? So if I could put the first name, the city, approximate age, and part of the phone number, and somehow the machine figures out who it is, hey, I'm just going to do that, right? Then I don't even have to bother to even have particularly good notes. I mean, for example, I personally don't own any kind of phone. I mean, phone books we have because they give them for free, but I never use them. Even in my phone, I don't necessarily need all the information about the contact because I can always go in Google and just throw enough words of the description of that person for Google to magically get me some close enough within 10 results of that, right? So this can be, in fact, extremely powerful, right? This is the reason, for example, why more and more organizations are not only supporting something like LDAP, but they are buying solutions, for example, from Google to do this kind of search for the purpose of naming, if nothing else, right? Not to mention that, and this is really powerful, I believe, and this is all about, in fact, naming and about guessing what I'm looking for. So the statistical analysis that can go behind the scenes can be extremely powerful. And I'm referring now to, for example, the autocompletes, right? So here is how I know if I'm asking the right thing on Google. It's not even about naming. It's not only that I look for a certain resource. I don't even know what I'm looking for. But as I type, Google is going to give me choices. If what I'm looking for shows up in the list of choices, I know is the right thing. And I just click on that, and it goes there, right? So especially this kind of mechanisms in which you're even trying to figure out what are possible choices for the naming as you type, as long as they are done interactively. Right, at the speed of the interaction, can tremendously help in this issue, resolve the name to some sort of a resource. Right? Especially when you're looking for programming advice. You can even tell how popular a particular programming language is by how good Google's matching algorithm is as you type along. Right? So, for example, I'm doing some programming in AngularJS now, and it's scary how popular it is, because almost anything you ask, the Google auto-completes everything. Right? OK? Now, this is really the universe in which all the name resolution is actually moving. Old way is to form some sort of hierarchies, the directories and whatnot. New way is to piggyback on some sort of search. Okay? That now starts to be applied even to local files, let alone files or other resources that live on the internet. If you're considering in the future to implement any such name mapping, you have to consider some sort of a powerful approximate search on top of forming a hierarchy. Because it's too hard to maintain the hierarchies in a good enough shape so the lookups don't actually fail, right? So the big problem, for example, with the DNS is the amount of effort required to keep everything consistent so that lookups don't fail even when you, in fact, have the correct names. Now, with Google, for example, all they need to do is rerun their approximate index building, whatever algorithm, let's say every couple of weeks or whatever it is that they are doing, and they're going to get a fresher version of the mapping itself. Okay? Right? Now, I don't want to spend more time on this. Anyway, we have only about a minute left. So this kind of concludes the discussion about the naming in general, the specific cases you have seen. I would encourage you to do at least a little bit of Wikipedia reading to kind of see more details if you're so inclined. I want to switch to synchronization, which is a completely different kind of issue and cannot be solved by just clever search that gives you probable answers and so on, right? a very, very delicate thing that it's at the core, in fact, of distributed systems, right? It's one of the best and the worst things that happen to systems in general, right? So it's going to be next week, synchronization. Okay. We're going to have a quiz now about all the naming. So I'm going to ask high-level questions in line with what you've seen before, right? The kind of questions you will not see is things like, how does this tiny itsy-bitsy thing in DNS works? But I might ask things like, what is DNS not about? Right? And then I throw some weird stuff in there and things of this sort. Okay? And when is the project due? Okay, Saturday. I'll also by Sunday Sunday night, post the new project because I want to make sure I maintain the momentum and you don't stop coding, right? That becomes important in itself. And good luck with the project. Just remember the tiny details don't matter. I get a lot of questions about is it this, is this, or this is this. None of them matters. Get me a nice simulation in there. Get some experience with how these things stick, difference between various topologies, and you're fine. Okay.